So this, you'll agree, is not a trivial thing to guess. But they use this for a random number generator because in this region it's pretty broad and almost uniform. Okay. By the way, this is also the density, pardon me? Density of? Yeah, I mean, even simpler, you know, if you go to these old shops, clock shops, and you see a lot of pendulum clocks doing this, most of the pendula are actually doing either this or this. When you take an instantaneous snapshot, assuming they're not synchronized. And the reason is that it moves very slowly when it comes to the ends and very fast when it's in the middle. So the likelihood of the pendulum being either here or here is much greater than it's being in the middle. That's if you took an instantaneous snapshot, you'd see that. But you instantly see that if you say theta equal to theta naught cos omega t, then t equal to 1 over omega cos inverse theta over theta naught. And I say, what's the probability density in the angular variable theta, given the fact that I take a snapshot at any instant of time, randomly in the time period, then the probability density in t multiplied by dt must be equal to the density in theta multiplied by d theta in modulus. And since this is just 1 over t dt equal to 1 over the probability density in theta d theta, you have T of theta equal to 1 over T modulus dt over d. And you can sit and normalize it and things like that. So dt over d theta is the time derivative of this. Time derivative of cos, I mean the derivative of cos inverse is 1 over square root of 1 minus. So this is proportional to 1 over square root of theta naught squared minus theta squared. That's this density. That's the same as this density. Shift to half. That's the density about theta equal to 0. If I shift to this midpoint, it's just exactly the same density. So what looks random in time, completely random, uniform density in time, in a changed variable is not uniform. This is well known. When you go from one random variable to a function of it, the density may look very different. And that's what is. So they use this. They use this thing here. And now it's an exercise for you to show that integral 0 to 1 dx rho of x log mod f prime of x is equal to log 2. So you can now at last calculate the invariant, the Lyapunov exponent for the logistic map at fully developed chaos. You know this rho of x, you need to put that in. You know this f of x, that's 4x times 1 minus x. Put that in, do this integral, and you should get log 2. That's the answer. Yeah.
So if you start from some arbitrary density,
right.
So if you take some time to relax to the steady state density.
Right.
So that density, is it given by the second eigenvalue of k, or is it related to?
Yeah, it is. Yeah, it is. So the correlations will involve the spectrum, full spectrum, and then you need to know the next eigenvalue itself. Absolutely.
Is that related to the Lyapunov exponent?
No, it's not related to the Lyapunov exponent. Not directly. No. In principle, this is a deep question because now we are asking, are recurrence times and so on related to the Lyapunov spectrum in a complicated system? In this particular problem, everything will involve log 2 and multiples of numbers times log 2. But in a real system, higher dimensional system, there's no simple relation between the relaxation times and the Lyapunov exponents. But there obviously is, there must be a relation. The reason is simple technical because if you want to look at recurrences, periodicity and so on, then or correlations, not only must the phase space point leave a certain region, but it should also come back. So its behavior both locally as well as globally in phase space are involved. Whereas exit times, relaxation times would be just leaving a particular point. So it's a little more intricate. But results are known for piecewise linear maps and so on. Maps with Markov partitions, etc. Some things are known. But it's not generally a simple relationship. Now, so this is left to you as an exercise to do this. Just one more example of an invariant measure and how messy the system can get. So this is the following. Is our cusp map. So let me write the solution for that too. And to find out what the map is. So the map is f of x equal to 1 minus twice square root of mod x minus 1 less than equal to x less than equal to 1. So it's convenient to take the map to run from minus 1 to 1 instead of plus 1 to 1. And then it's precisely the shape I wrote down earlier. This map starts at minus 1, has a unit tangent there, comes down, does this. So this is minus 1, 1, minus 1. This is symmetric. So this map is also chaotic, but it's intermittent here at this point. So you could ask, what's the density? Not surprisingly, the probability of being in this region is greater than being anywhere else. And the density in this problem, x, here's rho of x, is actually a linear function. So it's minus 1, 1, and this function is 1 minus x over 2. That's rho of x. And the map function is given here. So now, exercise is to show that lambda, the Lyapunov exponent, is integral minus 1 to 1 dx, rho of x, log mod f prime of x, where f of x is given by this function. And you've got to obviously do minus 1 to 0 first, and then 0 to 1. And if you do this integral, you'll end up with this is equal to pi squared over 6 log. No. This one will end up with equal to half. This particular problem, the cusp map, it's equal to half. Again, greater than half. No log here, it's just half. So, again, exercise. Check this out. And you could try to find the invariant density, this quantity, 1 minus x over 2, by writing the Frobenius-Perron equation in this case, that integral equation. I didn't mention that. This equation is it's the analog of the Liouville equation for the density matrix in this particular case. The equilibrium case is what it is. So write that equation down for this map, do the delta functions, find the functional equation, and verify that this is a solution. Now once you've done that, then put that in here and compute the Lyapunov exponent, and you should get a half. So although this is a very sticky region, because its injection region is appropriately adjusted, the density doesn't diverge. It's still finite. It's just a linear function. So it's a very useful model of type 1 intermittency. Just as the logistic map is a very useful model of fully developed chaos after the bifurcation sequence. And the Bernoulli shift is a paradigm of this sort of behavior. There's one more map I want to introduce, since it's not generally discussed in textbooks and so on, but a very interesting one. Just to show you how clever some people can be. And the map is the following. It's called the Gauss map. And what it is very simple. You start with the number x between 0 and 1. Take its reciprocal, 1 over x. That's of course bigger than 1. And subtract from it the integer part. So take a number, take its reciprocal, subtract integer. Keep repeatedly doing this. And then ask what sort of map do I get, what kind of fixed point, what kind of iteration, and so on. It's a chaotic map. Now what does the graph look like? Highly nonlinear. So here's 0 to 1, here's 1. Of course, the curve 1 over x is a rectangular hyperbola, so it's going like this. And now you're interested in x between 0 and 1, and you have to subtract the integer part. So when the number is between half and 1, you exceed this by 1. You subtract 1 and then you get this curve. The slope is always bigger than 1 except it's 1 at this point. Slope is minus 1 over x squared. Then between 1/3 and a half, you have to subtract 2. So you do that and then you get a discontinuity here, and then it's a steeper thing here. And between 1/4 and 1/3 you subtract 3, and then you get an even steeper thing, and so on. It's an infinite number of branches to this map. So it's an extremely nonlinear function. The pre-image of any point is an infinite set. Then the slope is always greater than 1 at all points except this. So it's immediately clear that the map is not going to have any stable periodic point or any stable orbit at all, periodic orbit of any period at all. It's also called the continuum fraction map. For the simple reason that if you wrote this number in the standard continuum fraction form, which I mentioned a little earlier, then if you start with x naught is 1 over a naught plus 1 over a1 plus 1 over a2 plus etc., where the a's are all positive integers, then it's clear this implies that x1 equal to 1 over a1 plus 1 over a2 plus 1 over a3 plus etc. So it's doing like the Bernoulli shift, except that you take a set of integers a0, a1, a2, etc., and map it to a1, a2, a3, etc. The knowledge of a0 is gone. And each time you're losing information about previous integer. So that's why it's called the continuum fraction map. It's doing pretty much like the Bernoulli shift, but you're doing this in continuum fractions. Now Gauss asked himself the following question. Suppose I take a number between 0 and 1, an irrational number, and I take its reciprocal, throw away the integer, take its reciprocal, throw away the integer, and keep doing this. Then what's the probability that the number I end up with after a long time is between 0 and some given number x, or some given number a, between 0 and 1. And then he thought long and hard about this. Apparently other people also were looking at this problem, and eventually he found the solution, and he said that the probability that the iterate x is less than equal to some given number a was equal to log 1 plus a over log 2. He was so excited by this result that he wrote to Laplace. He wrote a letter and said, I found this result, I've got it. Of course, I've not been able to find how he found it, but we can retrace backwards. It's a problem in finding the Frobenius-Perron equation and the solution. So let's do that. We can at least check his solution. So in this case, rho of x, we need the density. Once I find rho of x, I integrate from 0 to a and I should get a number there. This is equal to an integral from 0 to 1 dx, delta of x minus f of y, but x minus f of y is this 1 over y minus the integer part of it, times rho of y. That's equal to an infinite sum, because now you're going to have to sum over all the branches of this guy. You subtracted 1 here, 2 here, 3 here, 4 here, and you have to keep track of that. So it's equal to a delta function, a summation from n equal to 1 to infinity of rho of x minus f of y equal to x minus 1 over y minus some n, right? So it's 1 over y plus n, which implies that y equal to 1 over x plus n. So you have at least this here, definitely. And then it's multiplied by the Jacobian at that point. Now what's the slope of this guy? The slope is 1 over y squared is the slope, because the function f of y is 1 over y plus constant. So the slope is 1 over y squared, minus 1 over y squared. Take the modulus, it's 1 over y squared. You set x equal, so you have a 1 over y squared. And y is 1 over x plus n, so you end up with this. That's now the Frobenius-Perron equation written in functional form. And you'll agree it's not a trivial equation to solve. It's a functional equation. This messy form. But I don't know how that guy did it, but what he did was essentially to find a solution to this. And it's not hard for us to verify that rho of x equal to log, equal to 1 over 1 plus x log 2 is a normalized solution. You plug that in here, do partial fractions, etc., and then you end up with the same solution. So this is the invariant density, and of course you integrate this from 0 to a, you end up with this Gauss solution. So this continued fraction map also has very interesting properties, even more than the earlier maps, because it has an infinite number of leaves here. And you would expect, because the average slope is much larger, that the Lyapunov exponent itself becomes a little larger. Exercise. Use this rho of x and use the form of this function, 1 over x, etc., to show that the Lyapunov exponent in this problem, lambda equal to 0 to 1 dx rho of x log modulus f prime of x, but f of x is 1 over x, so f prime is 1 over x squared, modulus, etc. So log 1 over x squared, which is minus 2 log x. And the rho of x is whatever it is. This guy. So put this in and show that this answer, by the way, this Lyapunov exponent is positive. This is non-negative. X is between 0 and 1, so the minus sign outside, so it's positive. Turns out to be pi squared over 6 log 2. Pi squared over 6 rings a bell? Zeta of 2. There's a rational function and a log, so you expect zeta function to emerge immediately. And you can play with this integral, do it, etc. Show that it's this. By the way, there's another number theoretic significance to this. If you took any two random integers, positive integers, and asked, what's the probability that they are co-prime, the answer is 6 over pi squared. So it's related to that fact. This pi squared over 6 log 2 is related to that fact. Because the zeta function appears in these continued fraction quantities in various spaces. So one can play with this map as well and look at its properties, etc. There's a huge literature on the continued fraction map because it's an example of what's called a very hyperbolic, universally hyperbolic system. Now, what I want to do next is to go back a little bit and ask, what can we say about higher dimensional maps? What can we say about Hamiltonian flows, for example? Because all these maps don't preserve measure. All these fellows involve stretching, folding back, etc. They don't preserve measure. Can I mimic a conservative dynamical system using a map of this kind? You need at least 2 dimensions to do this because you want to conserve volumes and so on. And the famous Baker map does just that. So, Baker transformation. It's called the Baker's map because it's a map which mimics the way a baker kneads dough. So he takes this, he puts it back, he takes this, puts it back, and things get scrambled up in this space. It's a 2-dimensional map, so there are 2 variables, and the rule is xn is 2xn mod 1. The Bernoulli shift in one variable, but the yn variable equal to half yn n minus 1. Provided 0 less than equal to xn less than equal to half, and it's equal to half into 1 plus yn minus 1, or half less than xn less than. So it's slightly different map depending on what x is. Now, this map exhibits chaos, and you can kind of see what it's going to do almost by inspection. Because it will have now 2 directions, 2 Lyapunov exponents. So every volume element will get distorted, and you can look at the two orthogonal directions x and y and ask what happens in the x direction, what happens in the y direction. In the x direction there is stretching, so, and by a factor of 2. So it's clear that the Lyapunov exponent in the x direction will be log 2. In the y direction there is exact contraction by the compensating factor half, so the Lyapunov exponent would be log half. Therefore, the sum of the two Lyapunov exponents would be 0, which is another way of saying that the volume element will be preserved. Because there is exponential expansion in one direction, exponential contraction in the other, and the volume element is preserved. Now, we can see what the map does pictorially, because in the zeroth step, this is y and this is x, say. Take the unit square, and then this fellow goes in the next stage, after one iteration, to the following picture. It's expanded in the x direction, so, and contracted by a factor of 2. So it goes to twice its length, from 0 to 1 here, 0 to 1 here. It goes to 0 to 2 and 0 to half on this side. But you're supposed to take this portion of it, which corresponded to all those values of x which are on the right half after 1, and then add a half to the y variable. That's exactly equivalent to cutting this part and putting it on top there. So at the end of one time step, you have this picture.
So
Let's, yeah.
Will you please repeat?
Pardon?
Will you please repeat?
Yeah. So let's look at what this map does to the unit square in the xy plane. It says you contract in y, expand in x. I expand in x, I get double the thing, but I contract by a factor half in each case, and I get that long rectangle. But it also says whenever the original x was greater than half, which means it was in the second half, then you must add a half to the y variable. So that's like saying, cut that second portion of the rectangle and bring it back and put it on top of the first. So that the area is still 1, the unit square has gone to the unit square. But now keep track of where the points are. So let's start with some point, this is half, this is half. Let's start with some point here, say. It was less than half. So it's clearly in this box. And what is done is to move to twice its horizontal distance and half its vertical distance. So this point has gone to something like this. Some point here, what does that do? That thing there, first of all, it's to the right of half. So it's somewhere up here. And then it got extended to half its height. So it's somewhere here. Do this again, second time. Then you push this whole thing to the fore, this line, then you cut it in the middle and put it back again. So there will now be 4 compartments. So if initially to start with, I shaded this portion, let's keep track of the shaded box. That shaded box has gone here, and where has it gone now? It was all to the right. Therefore, this whole shaded box corresponds to that shaded box. So this box went to this guy. Now, where is the shaded box gone? You again stretched it. And where is the shaded box? In this case. Part of it is sitting there, and part of it is sitting here. In this case. Because some of this box had less than half, and some of this box had greater than half. They all got contracted by half, and then you cut and paste. And you do this again, it's clear that there's going to be more mixing. Portions from the initial thing get more and more mixed up. But you're absolutely guaranteed that every point of the initial square is still in this final square after any number of iterations, except that the points have got incredibly mixed up, horribly mixed up. And moreover, there is a loss of information in the sense that the Bernoulli shift in the x direction gives you a Lyapunov exponent of log. Now you can make this a dissipative system by saying, let's also contract it by a factor greater than half. Then the y box keeps shrinking all the time, and what you get is a striation of lines here completely, and it will become a fractal. So that's not a measure preserving flow. It's mixed, and it looks like a fractal object. Then you can associate different probability densities to different parts of the initial phase space and ask what's the final object going to look like after iterations, and you get what's known as a multifractal. So my intention now is to show you that once you have the invariant density, you get an infinite amount of pieces of information about the system itself if you now use the bandwidth which we are familiar with from thermodynamics, which is to calculate, once you have a probability density, you calculate a partition function, a free energy, and so on and so forth. So let's do that in the context of dynamical systems and see where it takes us. So I'm going to argue in the following way. In fact, I want to motivate partitions, so let me do that quickly. Let's go back to the Bernoulli shift, which is our simple canonical example. And then I should also explain what I mentioned earlier, namely, I said that this system is as random as a coin toss, and I must make that statement very precise. In what sense I mean that? So let's start with this Bernoulli shift and make the following scheme. I'll call 0 to half, I'll call it a box L, and half to 1, I'll call it a box R. Okay. And now my pretension is, my idea is, in a real dynamical system, I can't measure variables to an infinite degree of accuracy. I can only measure variables to some accuracy, some resolution. Therefore, automatically I have some graininess in phase space, and all I can tell you is, within a certain neighborhood of a point in a given cell, is the phase space point there or not? Is all I can tell you. And I keep track of that. In fact, in the general case, what one does is, here's the big phase space. I break it up into convenient sized cells. This is cell C1, C2, cell Cj, etc. And keep track of whether a given orbit is in a given cell or not. That's all I do. So, as I track this orbit, some crazy orbit going around, I end up with a sequence. I get C3, C6, C2, C5, I get a symbol sequence of some kind. That's my orbit. That's all the information I have. And then the question is, given this symbol sequence, can you reconstruct the orbit or not? And of course, you immediately say, in principle, of course, yes, provided the size of each cell is 0. If it's a point, then of course you track the full orbit automatically. But in practice, that's never the case. You have a certain finite size. And the question is, can you reconstruct the dynamics? And if so, to what extent? That comes under the purview of what's known as symbolic dynamics, and a great deal is known about it. But now look at what happens in this simple example. I have just two cells, left and right. I keep track of only whether the particle, whether the representative phase space point is between 0 and half or between half and 1. Nothing more than that. So if I start with an initial point, 0 point, A0, A1, A2, A0 is either 0 or 1 depending on whether it's in L or R. At the next stage, x1 is 0 point A1, A2, A3, etc. So A1 is 0 or 1 depending on whether it's L or R. Or it's L or R depending on whether A1 is 0 or 1, etc. So if I iterate for a long time, I'm going to get a huge sequence. L, 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 R, R, L, keeps going. That's all I keep track of. I simply keep track of whether it's L or R. And I get a long, infinite, in principle, infinite string of L's and R's. Now the statement, yeah?
I could not understand the role of size 0.
Size?
Size 0.
If the size of a cell is 0, that means I know exactly where it is.
Oh, yeah.
And then I keep track of it, I know the trajectory. That's the end. So that's never happens. Now, given the sequence of L's and R's, what does it look like? What kind of statement does it look like? Remember, this was generated by a deterministic rule, completely deterministic rule. Xn, 2xn minus 1. Totally deterministic rule. Now the statement about the Bernoulli shift being as random as a coin toss is to mean that given a string of L's and R's generated by a Bernoulli shift and given a string of L's and R's generated by tossing a coin and saying L whenever it's tails and R whenever it's heads. The precise statement is, given any string from a coin toss experiment, there exists an X naught such that that string is precisely the string generated by this deterministic rule. So for every random string you give me, I give you a string generated by a deterministic rule. And therefore the statement is